Hello, welcome to AP Calculus Lecture 3.7b, where we continue to talk about optimization. So using derivatives to find the maximums and minimums and to try to make the best decision that we can. So in your notes, the next, and we've got a lot of space to work this, but the next problem we have is a classic problem called the box problem. So it says an open box is made by removing the squares out of each corner of a 16 by 13 piece of cardboard. What size squares will maximize the area of the box? All right, let me show you what I mean by this. So I've already cut these squares out of a piece of paper here. I didn't do a very good job, not very uniform and not very crafty, but they're supposed to be the exact same size, all right? Cut these squares out. And then when you cut the squares out, if you fold like this, that's terrible, like this, and like this, you would have an open box. And we want to find the length or find the size of these squares, all right, that if we cut them out, it would maximize the volume of this open box. Okay, so let me go ahead now and draw the situation. So we've got, let's say it was this piece of paper before we had folded it. And I'll draw the squares that we're going to cut out in each corner. And let's call the side of each square just x. Since it's a square, they're both the same, right? X, x. And we know the whole length is 16 inches this way, the long way, and 13 inches on the short side. Now we know that volume is equal to, of a box, would be length times width times height. But we need to do that in terms of x's and 16s and 13s, right? So our volume would be, after we snip out these x's, it would be this length right here, this long length would be 16 minus 2x. And then this length here would be 13 minus 2x, or width. And then the height is just x, right? Because we snipped out the square, right? And each square has a side x. So when you tilt that up, when you fold it up like that, then the height is x. So multiply all that by x. All right, so I'm going to go ahead and FOIL this out. So 16 times 13 is 208. And then we'd have minus 26x minus 32x. I did the inside and the outside. And then plus the last 4x squared times x. Now let's distribute the x, and we have volume equals 208x. That'd be minus 58. Right? 26 plus 32 is 58x times x would be minus 58x squared plus 4x cubed. I'm going to go ahead and factor a 2 out. That'll be the same equation. So factoring out a 2, I'd have 104x. And this is just to make it simpler to work with. You don't have to do this. Minus 29x cubed, x squared, plus 2x cubed. And that's the best we can do. Now finally, we can take a derivative. So all the work in these problems happens before you take the derivative. So I'd have 104 minus 58x plus 6x squared. All right, and I can set that equal to 0. And I'm going to go ahead and factor out, I think I can, we don't have to factor anything out here, but we could probably factor, at least we could factor out a 2. But I'm going to go ahead and do 6x squared minus 58x plus 104 equals 0. And we'll use the quadratic formula. We got A, B, and C here. So the quadratic formula, remember, negative b plus or minus the square root of b squared minus 4ac all over 2a. So that's going to be negative 58, so that'd be positive 58 plus or minus the square root of negative 58 squared minus 4 times 6 times 104 all over 2 times 6. Now, if you don't mess up in your calculator, I'll go ahead and tell you what this ends up being. 58 plus or minus 29.5 over 12. And the two answers that gives you would be 7.29 inches, and it gives 2.375 inches. So which one do you pick? Well, remember, quadratic equations can give you extraneous roots. If you pick, and remember we're trying to find x, if you pick 7.29 and you snipped 7.29 away and 7.29 away, at least in this dimension, you'd have no cardboard left. It's too big because 7.29 times 2 is, over 14 and a half. That's greater than 13. So this is extraneous, and the answer would be 2.375 inches. So that would maximize the volume. And then if it did ask for the volume of the box, you would just plug those numbers in. 16 minus 2 times 2.375 times 13 minus 2 times 2.375 times 2.375, and that would give you the volume. But it didn't, it just asked which will maximize the volume, so you don't have to go back and plug anything in. But be careful, because on the test I might ask you to plug the numbers in on these types of problems and give me what the final volume is. All right, we got one more to do. So if you'll turn your page on the notes, we have got the cylinder problem. So I've got another, let's read through this. 120 square inches of material is used to make a cylindrical can. What dimensions, height and radius, will maximize the can's volume? And the volume is pi r squared h. Well, we have to put on our thinking cap a little bit here. How would I get the surface area of a can? Well, one thing that I've done, I just wanted to get a piece of paper, and I've made that into a cylindrical can, right? And the area of the top of the can would just be the area of a circle, pi r squared. And the area of the bottom would also be the same circle, pi r squared. Now, if you were to, we know that this is the height of the can from here to here. And then the width of the can, if we unfold it, this distance here, of course, this is height. And then this is width. But we've made it into a cylindrical can, which just means the top is a circle. So the width, that length, is just the circumference of this circle, 2 pi r. So width is just equal to 2 pi r. That's pretty cool. So the volume, so the area of the outside part of the can, the major surface area of the can, is going to be 2 pi r, the width, times the height, 2 pi r h. Plus you have that circle on top, pi r squared, plus another pi r squared for the bottom. So top, this is the bottom, and this would be the side of the can, all the way around. So that's the surface area. Okay, so let's go ahead and write that down, and we'll go ahead and draw a cylindrical can here. So here's our height. And then from the center to here would be radius. So surface area, and we know that the surface area adds up to 120 square inches. So we have 120 is equal to 2 pi rh, that's the sides, what we just did, plus pi r squared plus pi r squared, so that'd be 2 pi r squared. And we also know that the volume of the can, that's given in the problem, is pi r squared h. We want to maximize what dimensions, height, and radius will maximize the can's volume. So I've got to solve for either r or h and plug into the volume equation. It's going to be easier to solve for h because there's just one of them. Okay? So solving for h, I could bring that 2 pi r squared over to the left. So I have 120 minus 2 pi r squared is equal to 2 pi r h. So I brought that 2 pi r squared over to the left and subtract it. And then solving for h, I bring the 2 pi r underneath. So we have h is 120 minus 2 pi r squared over 2 pi r. And then I could factor a 2 out of everything and make it a little simpler. 60 minus pi r squared over pi r. That's h. So this one is quite a bit of work. This is worse than any of your homework problems for sure. Now I'm going to plug in right there for volume. So volume is equal to pi r squared times all of this. 60 minus pi r squared over pi r. So we just plugged in for h right there. Now some stuff cancels. This pi and that pi cancels. That radius cancels, and one of the radius cancels there. So you end up with volume is equal to just r times 60 minus pi r squared. All right. So we got 122 pi r. All right. Now, let's go ahead before I take the derivative, because we don't want to do a product rule. 60r minus pi r cubed. So I distributed the r. So the derivative would be 60 minus 3 pi r. We're going to set that equal to 0. So we'd have 60 is equal to 3 pi r. So 3 pi r squared. 3 times pi r squared, gotta have squared, sorry about that. R squared is equal to 60 over 3 pi, which would just be 20 over pi. So therefore, R is equal to the square root of 20 over pi, and let's go ahead and put that in decimal. So that would be 2.52 inches. So that is our answer for R. How would you get H? Well, you've got a formula for H, right? So H, we're just going to put that 2.52 right into here. It's going to be 60 minus pi times 2.52 squared over pi times 2.52. So if your calculator, your fingers don't betray you, that's going to be 5.05 inches is our height. So basically, a height that's twice the radius will maximize the volume of a cylindrical can. Okay, kind of like a cube, perfect cube maximize the volume of a rectangular solid that we found in the previous lecture. Okay, so let me talk about the homework for just a minute. So the homework is on the bottom of your notes. I'll go ahead and write it down again. And I've also got a couple of answers on that, but your homework is page 211. You can do 19A, 22, and 31. And the answer to 22 is given on your notes, and 19A and 31 would be in the back. So I just want to open the book up to those pages for just a second. All right, so 19A is a box problem. So you are just going to, they've already drawn it out for you. They've even told you it's 24 minus 2x. So they've got an x. So this is a square box. Each side is 24. So basically you know exactly how to work that problem. And you are to solve, you really all I want you to do is find the length of x that will maximize volume. Okay, so for 19A, just like we did, find x that will maximize volume. 22, I think, is pretty self-explanatory. They actually give you, you don't have to do much work on that one at all. They give you what y is, so, you know, and that is a rectangle, so you know that the area is just x times y, so you have to do a little substitution there and maximize that. For 31, they define what girth is. So a rectangular package to be sent by the Postal Service can have a maximum combined length and girth. Girth is the perimeter of a cross-section. Remember, and perimeter is given here in this red, so you would just add up those four sides and then add the length here. That has to add up to 108, so that needs to be in terms of x and y. And then, of course, volume. You know, we did this rectangular on number 17. Your volume equation would be similar to that, okay? So length times width. And, of course, it's, you know, x and x. So the top is going to be the same side. The top is just a square. So you're going to have a volume equation and then a girth equation that adds up to 108. And then you'll do a substitution and try to maximize the volume, find out what is x and what is y on 31. All right, that does it for this lecture, and I will talk to you on the homework solutions video.